Welcome everybody to our Integrability Journal Club. And today I'm happy to introduce Jingxiang Wu from Perimeter, who will tell us about Integrable Kondo lines for the IAM correspondence and for the Chern Simons. Jingxiang, please.
All right, thank you. Thank you for the kind invitation. So this work I'm going to talk about today is done in collaboration with my advisor, David Galloto, along with Jihong Li and Benoit Vicello. It's based on the following two papers. And like the title suggests, the talk is going to be about three different parts. The first part is about Integrable Kondo line defect, which is a particular line defect in 2D CFT. The second part is ODM correspondence. It's some statements about the Stokes data of the ordinary differential equation. The third one is a story about four-dimensional gauge theory called 4D Chern Simons theory. And there's actually a fourth part called Alpha and Golden model. But I will not talk about it today. The goal of this talk is trying to convince you, although they are very different, but you can use one to learn the other. Okay, the first one, the Kondo defect. So first, a few words about the defects in QFT. And they are very important and ubiquitous in the studies of quantum field theory. They can reveal hidden structures of the bulk theory. And for example, the topological line defect will carry the symmetry or even the category symmetry of the bulk theory. And the Kondo line defect I'm going to talk about today will carry the integrability structure of the conformal field theory. It's also a part of the definition of a QFT. So if you want to specify a QFT, often you have to do is you specify the set of local operators. But people have realized that over the years, you also need to tell me what are the large set of extended operators.
So sorry, excuse me. So your sound is not very good. Maybe can you try to switch between devices? Or if, I think you connected twice. Right? Maybe you can mute on one and.
I see.
Is it only for me because I can't hear very well?
No, for me as well.
Yeah, will be good if it's possible to improve.
Is it better now?
Yeah, a little bit better.
Okay, let me.
But it's still like a cave type of sound.
Okay, all right. So you share. Okay, all right. You can hear me right now, right?
Yeah, it is much better, I think.
Okay.
Yes, please continue.
As I was saying, the defect can be interesting on its own as well. They are often disguised as impurities, at mode, and difference in different physical systems. So I only talk about the defect today in 2D conformal field theories. Here, usually the defects are characterized by the behaviors of holomorphic or anti-holomorphic stress tensor across a defect. You can have topological line defects where the T and T bar are both continuous across a defect. You can have conformal defect, where the difference between T and T bar are continuous across a defect. You can also have a chiral defect, where only T bar component is continuous across a defect. And the Kondo line defect I'm talking about today will be a particular type of chiral defect. So generically, it's not conformal. So you need to study the defect RG flow. But if it happens to be conformal, then you can combine the last two conditions and you can derive the first one. So at the conformal fixed point, the chiral defect becomes topological line defect. So let me tell you what is the definition of Kondo defect. And today I'm only focusing on the case of the chiral SU2 level K WW model to be my bulk CFT. Although the generalizations to more generic rational conformal field theories should be straightforward. So the definition of the Kondo defect in the UV is defined as follows. So it's like a Wilson line in gauge theory. It's a trace of a path order exponential, and inside the integrand, you take the WW chiral current, JA, and you multiply with a bunch of matrices. The matrix will be the generators of SU2 in certain representations, and I will label the representation by its dimension n. So n will be 1, 2, okay, and so I integrate this contraction around the compact side circle of the cylinder, for example, and G is my coupling. And if you haven't seen this before, this is actually a well-studied object. It has a very precise physical origin in kinetic matter community. That is why it's called Kondo defect. It's about the study of magnetic impurities inside free fermion. So if you have a one-dimensional problem, one-dimensional spatial direction, and this is the time direction, and you have a magnetic impurity localized at a point, and now the Kondo defect is defined by this particular coupling between the magnetic impurity and basically your current. But today I will only focusing on the context of QFT and forget about the free fermion picture. In this context, it was started by Batras and Gabadil, and it turns out you can quantize this defect in a very nice way, in the sense that there are many symmetries that is nice and you can preserve. So for example, you have translation symmetry, both along and normal to the defect. You can still have chirality. In the definition in the UV, you only use the chiral current, and it will commute with the J bar component, and the renormalization doesn't spoil this fact. And you also have the global SU2 invariance. And this will resemble the case of XXX spin chain. So I have this marginal coupling G here, and you can study the RG flow. And it turns out on the next page, I will show you it will be marginal relevant. So you have a very interesting defect RG flow to study. So what is the beta function? It looks like this. So basically, you have asymptotic freedom in the UV, and as you go to IR, the coupling will increase. And so there's a dimensional transmutation happening. So you trade dimensionless coupling G into this dimensionful scale, e to the theta. So the scale lambda will be denoted as e to the theta. So now the Kondo line defect is really the one parameter family of line defect. And I will denote it, use this parameter theta. Theta is often called spectral parameter. Again, the n is a dimension of my representation of the spin. Okay, so it's strongly coupled in the IR, and it's very hard to know the infrared physics, but it turns out there's a very important result back in 30 years ago from Affleck and Ludwig. They gave us the what is the infrared behavior of this line defect. It turns out when n is smaller than k+1, the Kondo line defect will flow to a topological line defect. It's a particular topological line defect called the Valente lines. So let me recall that in the case of SU2 level K WW model, there are k+1 of them, and I will denote them by this curly L with the subscript 1 to k+1. Okay. But when A is bigger than k+1, the situation is different. You have the k+1 Valente lines, but you have something left over, basically. And that leftover part will still give me the Kondo line defect. And this will be referred to as overscreened or underscreened in the kinetic matter community.
Could you remind us a little bit about what Valente lines are?
So it's a particular type of topological lines in rational conformal field theories. It's labeled by, it has the same set of labels as the bulk primary field. So you have one for each WW primary. So for example, if you are familiar with conformal boundary conditions, in CFT, the Cardi type conformal boundary conditions is labeled by the primary, right? Bulk primary. For example, this one. And so if you have the Valente line is such that, for example, if you have a Valente line, sorry, if you have a Valente line labeled by this class label B, and you bring it to the boundary, it will become a boundary condition B cross A, for example. So it's a nice set of topological line defects.
Is there a simplification in the case of k=1 where this is just a boson, free boson at the self-dual radius, where you could make a clearer definition of what these operators are?
So you want to, it's like you want a Lagrangian description, right?
Yeah.
But you can, it's basically defined this way. So if you want the, from this result from Affleck and Ludwig, you can see this topological line defect is, you can find topological Valente lines in the IR of a Kondo line defect. So it's strongly coupled. It's not easy to define in explicit form. But if you want, you can think of this as a definition. So if you start with this UV description, and what you get in the IR is precisely my Valente lines. So you can think of this when G is at the conformal fixed point, will become my Valente line.
Thanks.
So that's why usually, so here I have G = 1. G star is like 1/k, or 2/k. So that is why usually sometimes people write it this way to denote the Valente line. But I think it's just a shorthand notation to remind people this is the IR line defect of the Kondo line defect. Any other questions?
And the statement that it will be conformal defect, it is conjecture, it is, so in principle it can be not conformal defect. Yes, some defect, but why it will have conformal here?
I think of, so I'm seeing like this suppose this is the RG flow, right? And yeah. I labeled my RG flow with this parameter theta.
Yeah.
And now I have a one parameter family of Kondo line defect. And so I'm saying, suppose you hit the IR fixed point. Yeah. And the question is, what are the line defect at this conformal fixed point? And the answer is given here.
Yeah, and it is conjecture.
It's conjecture, but it's, you know, it's confirmed by numerics and many other studies. So
yeah, okay.
Yeah.
Mm-hmm.
Yeah, as I remind you earlier, so once you add the conformal fixed point, the chiral defect become topological line defect. Okay. And of course, the miracle doesn't end here. It turns out the Kondo line defect is also integrable. And by that, I just mean it satisfies the following two set of equations. The first one is different Kondo line defect commute with each other. And the second one is usually called Hirota relations. And it's sort of like the fusion relations between different Kondo line defect. Okay. That is just my quick review of the Kondo defect. And next, I will tell you the other two parts of the story. Before I move on, is any questions?
Yeah, quick question. Now you have imaginary part, yes? So that was a parameter along renorm group flow, yes?
Yes.
Now you have imaginary part. So how you think about this object? Is just formal analytical continuation, or it is?
Yes, this is a great question. Indeed. So if I think of this, the physical meaning of the theta parameter to be the RG scale, it's not very natural to complexify this scale. But I do want to study for example, I want to study the value of this Kondo defect among some state. And this will be a analytic function of theta. I do want to study this function as a function of complex theta, but it's not very natural to study in the Kondo defect. And it will be advantage for the following two stories, because it will be much more natural to regard theta as a complex parameter in the other two stories. Nevertheless, you can find some physical meaning for this complex theta, even in the Kondo defect. So the first one is to remind you of this word identity. You can add this defect stress tensor to the defect, and now it will implement the RG transformation. You have some, like, you add this to along the defect, and you have some, for example, some coupling. And now the complex theta will correspond to complex lambda. So it's like I add this t hat to the defect with a complex parameter, and it turns out this complex parameter, it's like I rescale my defect in the imaginary direction. It will correspond to the rotation of the defect. If you look, roughly because of this one. But the punchline is the rescaling is implemented by the real direction of theta, and the imaginary part of the direct theta happens to be the rotation of the defect. There's a more more natural interpretation. Basically, the complex theta will correspond to the complex G coupling here, because I have this correspondence between these two, right? And so complex theta will give me complex G. And that is like studied this Hamiltonian system, but with a non-Hermitian Hamiltonian.
Mhm.
And that will that is like in physical system to study the interaction that with particle loss and dissipation, something like that. And indeed, it has been studied very recently by condensed matter people. And like you can also find some interpretation with this non-Hermitian Hamiltonian system.
Yeah, okay, thanks. But it still has sense to speak about IR limit for complex
Yeah.
state.
Yeah, you can still ask the same question, but the result of the F-Ludwig here is only about theta goes to positive infinity along the real lines. And now it's a natural question to ask, what about like imaginary theta?
Yeah.
Yeah. But you are totally right that it's not very natural to think of complex theta in the context of Kondo defect.
Mm-hmm. Yeah, thanks.
Okay.
I have a question.
Excuse me.
Sure. Sure.
Is there any other analyticity condition on this Tn as a function of theta?
So it will be it will be the transfer matrix, or the valve of this T will be the T functions. So you have the usual.
What do you mean usually? Is it monomorphic, no pole, or branch cuts?
So there's no cut. That's not that's an output. Like I don't require this, but there's no cut, for example, and there's no in the vacuum stage, there's no zeros in the physical strip. Basically, you have the usual statements of the T functions.
But usually it is at least in the simplest cases not pathological. It is assumed to be an entire function.
Yes.
An entire function, so which is quite well precise and so to say.
I should say that is an entire function of theta, and you can prove it rigorously. By the way, equation 7 appeared first in the work of BLZ.
Who is talking? Sergey, are you talking? I could imagine.
Yeah, and so these equations was actually introduced in describing these systems. And this
yes,
is
absolutely.
place where it appeared, the small first command. Then this is, you can rigorously prove that once how you define the defect, the T functions, that is in particular in your situations, that is an entire function of theta, right? And in theta plane. This is
Yes, and I will have, if Sergey has finished, I will have a question connected to the second condition in 6. Connected to the entireness of T. I could imagine, and the second equation in 6. Can you comment the second that commutativity relation a little bit on?
Sure. Yes. So
it's a sort of Hamiltonian or moment.
Yes, exactly. Yes, this is basically saying when you quantize this line defect, you have the translation invariance normal to the defect, basically. I was just trying to say this fact. You can translate. There's a rigid translation, normal to the defect.
But has this to do also with conserved charges and commutativity of conserved charges, local interaction motion, things like that? Non-local charges and so on?
No.
Of course, everything seems to be at the conformal point so far. Am I right?
Oh, no. The line defect itself is not conformal. I have
yes,
scale on the defect.
Yes, that's true.
Yeah, but yes, if you like, you can think of this commutativity as only the first one. I only, yeah, this
exactly that was also my question. Yes.
Yeah. This is just to say the equation form for that translation invariance.
Okay. Thank you very much.
And by the way, this commutativity means, for example, that if we take a vacuum, it will be eigenfunction of this T will be G function, more or less.
Yes. Up to normalizations. Yeah.
Oh, yeah, up to something. And in principle, G function for non-vacuum states. So if you take another, it also commute, and there will be some another eigenvalue, probably. Yes.
Yes.
Mm-hmm.
Okay. Now let me move on to the second part of the talk. So what is ODM correspondence? It's quite easy to phrase in the language of the Kondo defect. It's basically when you try to study, when you try to calculate the expectation value of Kondo defect in a particular state of my CFT, it can be also computed from the Stokes data of some other ordinary differential equation. And this ordinary differential equation at first sight has nothing to do with my conformal field theory. And this sort of equation is the statement of the correspondence. And I will show you the precise statement on the next slide. But before that, let me just give you a flavor. This is the very first example of the ODM correspondence. And so you have for the quantum SL2 KdV, you have this second order differential equation. It's a differential equation in the variable x. And now here I will refer to as the potential part, just like in the Schrodinger equation. And here the potential is like a polynomial form. All right. So to my knowledge, the physical meaning behind this correspondence is still unknown. That is why it's very mysterious, and it's also the part of the motivation of this project. So let me explain what precisely is this correspondence using the examples started in our paper. So I claim for the chiral SU2 level K WW model, the ODE is given by this. So what does it mean by this is given by the ODE? So this is the ODE, and you try to study the solution of this ODE. Let me just explain the potential first. Okay, so now you have a parameter theta part, and what's different from the KdV case is you have the exponential part e to the 2x, and now you have x to the k, where k is the level of the WW model. You also have a small t of x, which I will explain below. So now let me just remove the first part. Okay, I have an ODE with a parameter theta and k. So the statement is that first you find the unique solution, which I call psi zero, that decays exponentially fast as you go to the positive infinity. You find the solution, and you shift the theta parameter by this amount, you shift the theta parameter by opposite amount, and you calculate the Wronskian between these two, where the Wronskian between two functions is just simply defined by this. So I will introduce this shorthand notation by so if I shift the theta parameter by n pi I, I will use this subscript n here. So this big object will be denoted by this. And this, the Wronskian will be independent of the x parameter, but it will be a function of theta. Okay. And the statement that this function as a function of theta will be precisely the vacuum expectation value of my Kondo line defect. Okay. So what about the other state? So suppose I want to study some generic state phi, and what about the expectation value? In this case, I have to add this small t of x, and I will parameterize this t of x in the following way. It's a squared plus partial a, where this a is as follows, and it has a few parameters. I have alpha here, I have L, I have a bunch of WI's, and I have a bunch of WI primes. So I will not give you the details, but actually the techniques to find excited state is more or less understood from all those studies. But the basic strategies is, suppose you give me a generic state phi in the spectrum, and I will have a, I will have a dictionary that tells me what is the value of alpha, what is the value of L, and number of WI, and number of WI prime. Now, what's left to specify this L of X is the precise location of WI and WI prime. And that will be determined by a set of rational equations, and often called Bethe equation.
Excuse me, the second sum on A, so W prime is index A, maybe. Okay, yes. Thank you.
Yeah, that's
Could I also ask, so you show how to construct T out of psi. Is there an inverse map? If I know T, how do I find psi?
If I, in this phi, this state?
Well, in any state, even for the vacuum, right? So yeah, you have a map between psi to T.
Oh, this state, right? So you are saying, can I reverse the arrow here?
No, I'm saying, so once you know psi, you know you build Wronskian, and this gives you T of theta, right?
Yes.
So is there an inverse map from T of theta, or I don't know, Q of theta to get psi?
Not that I'm aware of. I don't think so, because the T.
I'm sorry to interrupt you, but perhaps the simplest way to do this is extract the value of local integral of motion from the large T asymptotics, and then you the large this local integral of motion is certain symmetric symmetric functions of W eta. In principle, then you reconstruct W eta and then reconstruct the potential. Well, it's for the lowest levels you can do this. It's rather straightforward, but in general, that's a good point.
Yeah, just I mean, so there is so this correspondence, but it looks like it goes one way easier than another, right? So just. Yeah.
But in general, in principle, this is kind of inverse scattering problem, right? You know the connection coefficients, and you you should reconstruct the potential.
Okay.
Right, and but if you look in the solution in the certain class of potential, right, that basically reduced to the algebraic problem, at least for the simplest situations.
But okay. But is it guaranteed that well, I will find
yeah, that is miracle. It looks like a miracle that indeed you, because the number of states, you know, that's a, well, it's not arbitrary, right? For example, the number of solutions of the number of value of wi in the formula 8. So they labeled the states, right? So so it's a kind of highly non-trivial statement that the algebraic systems will have the certain number of solutions. But well, of course, there is no mathematically, it's not proven, at least the simplest situations, but in general, it's not clear.
Okay, thank you.
Thanks for the comment. So
sorry, and another question. Sorry, I have
yes,
many
please.
questions. And Hirota equation, is it guaranteed from the Wronskian formula? Is it? Or
it is.
So in principle, it's only what is only T1, which is kind of informative, right? For the inverse, for the inversion purposes, I only need to use T1, I guess. But okay, thanks.
I will explain what is the Hirota relation from this ODE perspective. But let me just finish the presentation here. So I was saying, like, you have a bunch of equations called beta equation. It's basically a set of equations such that my ODE has trivial monodromy around all the omega I and omega n primes. And you basically solve this beta equation, and you get the location of wi and wi prime. And now I fix this a of x. Now I just go back to my ODE. I calculate, I find that solution psi 0 that decays the fastest, and I calculate the Wronskian again, and it will give me the vacuum that give me the expectation value of my Kondo defect in that particular state. So suppose that I hand you this correspondence, and I for some reason it's true, then there are some obvious advantages to study this ODE over the Kondo defect, which is a description in the UV in the QFT context, because as we already discussed earlier, in the study of ODE, it's quite natural to study this differential equation with a complex parameter theta and complex k, for example. Whereas in the Kondo defect, the complex k will correspond to the study of representation of Cosmodi algebra, and complex theta will be less natural. But as in the study of ODE, we are in a more natural situation to study the analytical properties of the Wronskians, for example. But what kind of checks we can do to verify the claim? So of course, the very first one is try to do the calculations on both sides and try to calculate the function and compare them if they agree or not. And we did the calculation in the first few orders of the coupling G, and they match exactly. Okay, so the second check we can do is try to reproduce the infrared phase diagram.
But could I ask, so why do you need to do it state by state? I mean, so you can prove it does satisfy Hirota. You can prove that it has certain analytic properties. So then you just like need to mimic certain characteristic of the state, and then that's it. No, why? What is still mysterious about it? I mean, inverse way is a bit mysterious, maybe, but going from ODE to to T of theta, you explained was quite unmysterious, no?
Yes, but are you saying like the following checks are not independent? But I just want to do more than just verify the T functions on both sides satisfy the same functional relation.
Because normally if you have functional relation plus analyticity, in all cases, I know it's sufficient to prove that's identical.
Sure.
It's not very mysterious, at least to me. Or can you like tell why it is mysterious?
The mysterious part is for example, the physical origin behind this. If I give you CFT, or if I give you in more general case integral field theory, what is the meaning of this P of X, this potential, and is there any physical meaning for this variable X, and is there any physical meaning behind this wave function? This is the question I'm asking. But it's true that it's not very hard to reproduce the same set of functional relations on both sides once I give you this ODE. That is indeed the fourth point. The Wronskians from the ODE will satisfy some relations, often called plot relation, that will give me the same set of functional relations. Yes. So all those points are on the one hand try to verify the claim. On the other hand, suppose the ODE is correct, then I can use the ODE to study my Kondo defect. For example, the second one, I can try to study this Wronskian on the ODE side and see if I can reproduce the infrared phase diagram from the Kondo side, which is quite hard from the Kondo side, right? It's in the strongly coupled region. But we can actually do this. I will explain on the next slide. And so of course we can also try to find if we can reproduce all the states in the spectrum, and that will be another check. And the final point I want to mention is we actually can reproduce the beta function. So if I give you this ODE, suppose it's true, I can also find the beta function out of this ODE. But to calculate beta function from the Kondo side, although it's straightforward, but it requires a very tedious and painful calculation of normal ordering. It's a usual renormalizing procedure, but it's a very long calculation.
But from functional, from say Hirota equation, you can probably write something like TBA and then find it, solve it, right? And find beta function. So convert functional equations, Hirota equation, into TBA type of or some integral type of equation, and then you can compute whatever you want directly from there, never relying on ODE part.
Sure. Yes. If you yes. If you have the once you have the TBA, you can sure. You can also do calculations from the TBA side.
But TBA is just Hirota plus analyticity, nothing else, right? So once you know that your T of theta has certain asymptotics, don't have poles or zeros, then you can derive integral equation and do whatever you want. I don't know whether it was done in this particular case.
Is it clear to you how to get the beta function? The beta function is like the G, right? So there's like this. from the TBA side?
Well, maybe I missed what is the relation of that to T of theta?
Actually, maybe we will slightly postpone this discussion to coffee break, which is actually should start more or less in this time. If you will find some point to stop for coffee break, we then could proceed this discussion.
Okay. So let me, I think I can quickly finish the next few slides and we can, when is a coffee break?
Coffee break, well, in principle, more or less now, but if you need a few minutes, it's absolutely fine.
Yeah, let me just finish this one. Okay,
Yeah,
then we can. As I was saying, the renormalization procedure in the UV is quite straightforward, and you can do this. And the basic recipe is given by the Bacha-Scapadieu, but the calculation is very hard, even with Mathematica. So at the fourth order, it's already a very long expression, and if I give you this, even I give you this expression of the fourth order, to calculate the expectation value, it still needs a long Mathematica notebook. So anyway, but to do the calculation from the ODE side, it's quite simple because I'm just trying to find the perturbative solutions in small g and try to do the calculations in the Wronskian side. So the point I want to make is basically we can do similar things in different side of the stories, but once I give you this ODE, it's often easier to do the calculation on the ODE side. And I can use this ODE to learn the physics of a Kondo side.
Sorry, I just missed the notation. G is what, 1 over theta or something like that?
Oh no, G is related to theta in so G is
Okay, makes sense.
So yeah, this is a scale. So yes, now we can do the coffee break.
We can do the coffee break.
Yes.
Ah, great, thanks. So if
just a naive question about this slide, is theta to minus infinity or plus infinity? It's minus infinity, right? In the bottom.
You can use different conventions, but for me, IR means theta goes to positive infinity. So the scale is.
I thought we were discussing a small g expansion, right?
Oh yeah. So here is a UV. On this slide, it's UV expansion where g is small. Yes. This is separate.
Okay. Okay, so that's high temperature of TBA, right? That's the one that normally is a bit harder to extract corrections from TBA, right?
Yeah.
Mm.
Okay.
Okay, any other questions?
Right, should I pause the coffee break?
Yes, and can you pause?
Cool. So I want to explain how do I reproduce the infrared phase diagram from the ODE, and what do we need to do? So the conjecture made by Effler and Ludwig is the follows, right? And depend on n is bigger or smaller than k+1, I have different infrared behavior. And suppose I starting the vacuum expectation value, and different validity lines have different vacuum expectation value. In particular, when n is smaller than k plus 1, I have this sum function over another sum function. It's usually referred to as a quantum dimension. But when n is bigger than k plus 1, I have this, but this part give me 1. So the k plus 1, the value of k plus 1 validity lines give me 1. And this part just give, at leading order, just give me the dimension of my spin, which is n minus k. It's an integer. So our job is try to study the ODE and find the large data of the large data in the large data limit, find the Wronskian, and see if we can reproduce this different behavior for different n compared to k plus 1. The techniques to do this is more or less standard. It's called exact WKB analysis. So what is the rough idea here? So instead of considering my ODE on the real line, so before the x is real, but now I consider my x to be a complex number. I have I only focus on the case of vacuum case. So in particular, small t of x is 0. So I only have this ODE. And so the first thing you do is to read off the potential, and that is referred to as the quadratic differential. And I have this quadratic differential. I can define a diagram called a WKB diagram. So this is on the x plane. And the diagram is the union of a bunch of curves. The blue curves shown here. And the definition of the curve is such that the tangent vector of the curve contracted with the one form is a real number as opposed to a complex number. So now you have a bunch of curves. You have you find this WKB diagram, and it has some other names. For example, Stokes diagram and the spectral network. Etc. So the expert in the audience might find this diagram quite weird because it's quite unusual. For example, usually the Stokes diagram, so I have it's basically defined by this quadratic differential, right? And
sorry, just to get some intelligence, the dot is the turning point, or is it?
Yes. So I have zeros of the quadratic differential. I have singularities, and 0 is a turning point, which is this dot here. And usually we study a simple 0. So starting from a 0, there are 3 lines coming out. But now I have higher order 0, order k here. That's why I have more than 3 lines coming out of this 0. In the current case, it's k equals 3, I believe. Okay, so
sorry, but what you define is dotted lines, right? Is a WKB diagram, not the solid lines. Solid lines, something else, right?
Yes, I want to explain that. So usually the WKB lines start from a 0 and end on the singularity, but that's not the case here. Because of the exponential part, we can actually have Stokes lines starting from negative infinity to positive infinity. This doesn't happen in other Stokes diagram. Because of this, we have to generalize the usual exact WKB analysis, but it can be done. And I will not bore you with the details. Let me just mention a few facts from the studies. So, for example, along each line going to infinity here, you can find a unique solution that decays the fastest. For example, we defined the psi 0, right, previously. And that is the one that decays the fastest, exponentially fast along the real line. And it so happens that the psi n defined this way will be the solutions that decays the fastest along the each WKB lines into infinity. So now I want to study the Wronskins between all those solutions, right? And it turns out the Wronskins have very different behavior. And so what you do is you look at, so for example, if I want to study the Wronskin psi 0 and psi 1, and I look at which lines they associate to. Here, okay, it's the red line.
Can I ask just a naive question? So the main novelty in this analysis compared to other ODE-IM studies is this exponential dependence in X. Is it true, or am I confusing this thing?
Yeah, yes, yeah.
I see. And that's the main thing that allows to have all these various asymptotics separated by pi. It's because of that exponential, right?
Precisely, yes.
Yes. So that's the main novelty, right? Before it was mostly polynomials or something like that. But with this exponential, you have this new ingredient, right? This all this.
Infinitely many sectors kind of before
but it's the same equation. You can write in polynomial form, in exponential form. It's more convenient for WKB because the problem, as usual, because centripetal potential, you know, it's not the WKB not applicable for in polynomial form. But in exponential form, it's much straightforward, much more convenient. But it's the same equation. You can write this equation in polynomial form. But it's not, it's just, you know, coordinate, you change the...
But then it won't be issued in the equation, right?
This equation, well, in general, well, you know, if you consider, well, this equation contains exponent, but anisotropic, if you consider the anisotropic Kondo model, then it would be polynomial equations. If you do the calculation in anisotropic Kondo model, then it's straightforward to just take a limit in isotropic case. So that isn't, you know, the matter. It's not conceptual problem when this point. The exponential on because it's more than the same. It's just a standard WKB. It's not a special, nothing special in this WKB.
No, of course, I'm not saying that you need to read Ved physics to study exponentials. I'm saying that usual.
And what I say that in principle the analysis is simpler to do. It's an isotropic case when they have a polynomial, and then they perform the limit just on the end of the story. And this is an isotropic. It's this usual because you know this is the same situation because here we have a asymptotic free theorem, but if you have a marginally relevant perturbations, but it's of course it's better to work in super normalizable field theory, and where the perturbation then it's simpler. The physics is simpler. So that in principle you can do this without the exponent can be appeared only in the end of the story. So that is not. Yeah. That's only the point.
Could I maybe suggest that we postpone this for afterwards, and because I think we're getting to the good bit, right, Xinjiang?
Okay. Sure. Let me just quickly finish what I want to see here. So it turns out if you look at the diagram and if the Stokes lines it associated to connect to 0, it will the leading order behavior in the asymptotics will be the quantum dimension. But if you calculate the Wronskin between solutions that are associated to the lines that connected at infinity, negative infinity, it will be an integer, and that this will reproduce the Kondo side analysis. Okay, and this condition of connected at 0 or negative infinity is precisely the condition n smaller than k plus 1 or n bigger than k plus 1. So yeah, we just reproduce the infrared phase diagram. Let me just quickly say a few words about the constructions in 40 Chern Simons. As I said, I want to explain the more physically what is the origin of this ODE and so on. And we made an attempt in the construction of 4D Chern Simons. So let me just give you a very quick review of 4D Chern Simons. It's like a 3D Chern Simons, but in a 4-dimensional spacetime. And here, the spacetime is R2 cross C, where the R2 direction is usually referred to as topological direction. And I will use the coordinate X and Y. And the C direction is usually called holomorphic plane. And I will use the Z coordinate. Okay, what's the action? Action is the usual Chern Simons 3 form, and which a holomorphic 1 form dz. But the connection A is not a connection. It's only a partial connection because it's missing the AZ component. And so you can do the analysis. The quantization is not entirely obvious, but it was showed by Costello and later by many other people. You have the topological behavior in the R2 direction and the holomorphic in the C direction. And the simplest operator you want to study is Wilson lines, just like in ordinary 3D Chern Simons. It has been shown in many examples. This is a good, a framework to study the integral model. It often gives you an intuitive picture in the gauge theory language. But you have to be careful because this theory is only defined perturbatively. So if you want to make a non-perturbative statement, you might as well study the string theory construction of the 4D Chern Simons. But other than that, in the framework of perturbation theory, it was shown by Costello that it's well defined and it made a nice quantization. Okay, how do we realize Kondo problems? So what you do is along the topological plane, XY direction, you put a surface defect. On the surface defect, I put a chiral WW model. It's located at a particular point Z0 inside the C. Okay. Now it coupled to the bulk via this coupling. Where is the Kondo lines? It's realized by the Wilson lines parallel to the plane here. And once the idea is once you get rid of the transverse Z direction, it will become the Kondo lines in the 2D theory. There's one important thing you have to be careful about because it's known that once you like the chiral WW model has a gauge anomaly when you try to couple to the gauge field, and you need to cancel that gauge anomaly. The way to do that is to change my, so I use a 1 form to define my action, the 4D action. The way to cancel the gauge anomaly is to use a different 1 form, basically the shift by this amount. After the shift, this 1 form is not closed anymore. So the bulk for the 4D is not gauge invariant, but precisely that this gauge anomaly is canceled by the gauge anomaly from the WW part. Now we have a well-defined theory without any gauge anomaly. So, like I want to stress that now the action is really replaced by omega z by a different 1 form. Once I add this surface defect. How do I implement the RG transformation? There's an unpublished result from Costello that the RG transformation can be implemented in a very nice way, very intuitively. So basically, what you do is you fix the position of the surface defect, and you have a Wilson line, right? The RG flow is basically translating the position of the Wilson lines while fixing the position of the surface defect. More precisely, it's not shifting Z, but shifting the theta parameter, where theta is like the local coordinate. It's a primitive of this one form. And like the name suggests, I want to identify this theta with the theta in the ODE and with the theta in the Kondo line defect. Okay. Why do we get back the Kondo lines? And some checks are very automatic. We get the commutativity of the Kondo line defect essentially because they are realized by the Wilson lines in the bulk, and the Wilson lines are located at different positions in the complex plane, so I can commute them. And Hirschheimer relations is realized by the fusions of Wilson lines. And you can study the fusion of Wilson line in the bulk, and that will give me precisely the same equation of the Hirschheimer relation. The point I want to explain a bit more is the how do we get the beta function out of this? So, so I have this surface defect here, and I have this line. So the leading order interaction, the effective action is caused by this gluon exchange. And if you calculate this, that will give me this term in the action. And if you recall, the way I defined the Kondo line defect is G, this is the coupling, and the matrix TA and JA. Right. So now what I need to do is just basically identify this 1 over the distance with the coupling G. But I know the relation between Z and theta from this relation. So now I can know the relation between how G depends on theta, basically. And this is precisely my beta function.
Sorry, but so far there is little surprise, right? Because you have Wilson line here and there, it's just like identification of parameters.
Yes, yes. But this is one of the first like renormalization in the foundation Simons, because you have to I guess the meat is this result, I guess. How you do the RG flow in foundation Simons, basically. We started this journey because we want to understand the physical origin, and we want to ask the question of physical origin of the ODE correspondence, and we want to find some answers from the 40 Chern Simons. For now, we haven't found it. The best I can say is we found this this matching between two quantities in two sides. So let me remind you that I have a Kondo, I have ODE, and the second part is basically studying the relation between those two. And I have 40 Chern Simons. I tell you the relation, how do I go from 40 Chern Simons to Kondo lines? And could I find the relation just directly between ODE and 40 Chern Simons? So it turns out the one form I use is the follows, right? It will give me precisely the twisted one form using in the ODE. So the twisted one form is defined as follows, and they match the form of this one form match exactly. But of course, the origin of this matching is still eluding us. But since we have this matching, I believe if we go to the string theory construction of 40 Chern Simons, we might be able to explain where there's a matching is coming from. But right now it's still unknown.
18 is for the vacuum. Or not?
No, this is a statement of the one form, so it has nothing to do with vacuum. But you are right that it's not. So you might want to ask the question that so how do I study excited state in for Chern Simons?
So it is
that,
vacuum. Okay.
Yes, that one is not clear to us. That's a very good question. Yes. That's like asking what is the how do I explain base root? So I have a of x and I have that, right? I have the x minus omega. How do I explain the wi prime? Yeah. Okay. So before I conclude, let me just mention the very first generalization you can do. So what about you have a product of SU2 WW model, and what you get in the three different parts, pretty straightforward. So to define the Kondo line, you just have one coupling for each SU2 factor. So this I denote the different SU2 factor, and I have one coupling for each SWW current. But note that they are coupled to the same impurity, same spin. So ODE is also simple to write down. You just have one factor for each SU2 factor of WW model. In the construction of Chern Simons, what you do is you, instead of one surface defect, you put multiple surface defect, one for each factor of SU2, and they are located at different positions of ZI, Z1, Z2, Z3. And correspondingly, if you want to cancel the gauge anomaly, you have to use this one form. And the Kondo line is realized by a single Kondo, a single Wilson lines in the bulk. And the statement of Costello is basically when you do the RG flow, the position of surface defect doesn't move. You only move this Wilson line. Okay. So let me just conclude that today I've explained to you a few different stories, Kondo line defect in CFT, and I found OPER, which is a mathematical term for the ODE I'm studying, and the Chern Simons. There's a different story, I can go that model I haven't told you. So we studied the detailed properties of this ODE and try to study the physics out of it, the physics, the Kondo side of physics from this ODE, and doing some detailed calculations and how it gave us back the Kondo side. And usually, as we see earlier from my discussion, the calculation in the ODE side is much easier from the Kondo side. And we can even do some calculations in the strongly coupled regime, whereas the strongly coupled Kondo model is quite hard to investigate. Although we are not quite yet, I believe we can try to explain the physical origin of this ODE from a string theory embedding of Chern Simons, because we have that matching between the twisted one form. And there are many future directions as well. And obvious ones, for example, you can try to do higher, like more general Lie algebras. You can also do cosets, which will give you the minimal model. You can, as Sergey already mentioned, you can also do anisotropic Kondo problem that will break the SU2 global symmetry. A more drastic drastic change would to study the massive ODE-IM correspondence. That will give me the Kondo lines instead of in CFT, but in an integrable field theory. More precisely, for WW model, that will correspond to the chiral Gaussian view model. And the ODE-arm correspondence is replaced by the Hitchin equation, for example. And finally, we really want to explain the ODE-arm correspondence, but we might need to go to the string theory construction to resolve this problem. And with that, let me just end here and thank you for your attention and all those questions. Thank you.
Thank you. Let's unmute ourselves and thanks, Jingxiang. And now questions, please, comments.
Sorry, maybe I missed the point. You did not discuss this string embedding in your talk, did you? If you
No,
did,
no,
okay.
that would be one of
Can you say a few more words about it? What is this?
So there's a like quite a famous construction from Witten using the D3 and D5 system to realize the analytic continued 3D Chern Simons, and where the 3D Chern Simons is realized at the boundary of D3 brane. And now the obvious starting point would be try to use the default D5 system. And on the boundary of, so suppose I have a bunch of D4 branes. On the boundary, I would have.
Sorry, do you mean NS5 brane? You can't have D4s and D5s together normally?
Sure. Sorry. Yes. Sure.
Sorry, but how would it kind of reveal physical origin? It seems you are embedding some, I mean, not too complicated algebraic construction into more complicated field theory and then into string theory. That's the next step. How will it make things clear? If it's already just Schrödinger equation, why do you want to make it into something much more complicated to explain the physics? Like a just philosophical question. I don't quite see like how in principle this could explain anything. I mean, what needs to be explained, to be honest, right? So there is this formula, you plug one to another, you get the right result. So why? What else do you need to explain?
For example, if there is a physical meaning behind this P of X, and like the quick answer would be try to explain that matching between the one form. For example, I have the one form in 4D Chern Simons, I have the one form from the ODE side, and why there's two. The hope is try to get this from S dualities, from dualities in string theory, for example. It is like I find generalization.
Sorry, but it's not explaining this, like kind of creating a new relation, right? Just by considering a third type.
No, but this is just meant to be a non-perturbative completion, right? String theory is good, everything else is bad, and you know, ultimately,
I'm pretty happy
if you can embed it into string. If you can embed it into string theory, you have a consistent quantum theory, right? That would tell you non-perturbatively what happens.
Well, I thought Schrödinger equation is pretty consistent quantum theory without.